Next, let's discuss the average power of periodic signals. We suppose the voltage and the current of one component are with associated reference directions, and they have been expanded into the sum of DC and every harmonic wave by Fourier series. According to the definition of the average power, it equals the integral of the instantaneous power in one fundamental wave period over the fundamental wave period. The integral term also has four parts. The first is a product of two DC components. The integral part is a constant, and it equals this. The second is the integral of the product of DC current and every harmonic voltage. Similar to the previous discussion, the integral of these components are all zero, so it equals 0. The third is the integral of the product of DC voltage and every harmonic current. Similarly, the integral of these components are all 0, so it equals 0. The fourth is the product of the current and the voltage of one harmonic. By applying trigonometric transformation, we know this part equals this. Similarly, the integral of this part is 0, so the integral part is a constant. Theta Ku minus theta Ki is the initial phase angle difference between the case harmonic voltage and current, and it's defined as theta K. So it equals this. UMK is the maximum value of case harmonic voltage, and UK is the effective value of case harmonic voltage. IMK and IK have similar meanings. By adding them together, we know the average power equals this. This conclusion is easy to remember. Under the effect of periodical non-sinusoidal excitation, the average power absorbed by one element equals the sum of the absorbed power at every frequency. In other words, only same frequency produces power. Next, we use the conclusion to analyze a simple question. The voltage signal has DC components, fundamental wave, second harmonic, and third harmonic. The current has DC component, fundamental wave, and second harmonic. We need to find the absorbed average power and the RMS for voltage and current. Firstly, let's solve the average power. You see, this part is a DC power, this part is a fundamental wave power, this part is a second harmonic power, and this part is a third harmonic power. Then we solve the RMS for the voltage. Then we solve the RMS for the current. In the calculation of RMS for the branch variables and the average absorbed power, you may have a mistake. You should notice the maximum value in the time domain expression should be transformed into the effective value in the calculation. Well, this is the end of this lecture.